Hello. Hey guys, how are you? Hope you guys are enjoying the conference as much as I am today. Quick question for you guys. Just quick raise of hands. How many guys use Phoenix? Cool. And how many guys use Edgebase as well without Phoenix? Good personal question that we can tack on later is like why, but let's do that later. For now, let me introduce myself. My name is Anirudha Jadhav. I go by Ani. Today's talk will primarily focus on our query infrastructure and how do we scale hundreds of developers and multiple applications using Phoenix at our company, and give out some ideal architectures and the work that we have done to make it even simpler and integrations with Spring Boot. Now, how many of you guys over here use Spring Boot or know about Spring Boot? Okay, quite a few, not as much as I would have expected, but yeah, that'll be something new today then. So let's go ahead. But before I go ahead, I want to actually give out a special thanks to some of our teams internally, primarily Ritesh and Clay and the Bark team, everybody over there, and Artem with Hortonworks, who has been helping us through our Phoenix and Edgebase work going around. With that out of the way, definitely stay put for the entire presentation because we have a lot of demos that will explain and show through live actions. So I think everybody knows Bloomberg. I'll just give a brief introduction. We are a financial data company. At a core, we are an information company. We deal with a lot of different use cases, which gives us a chance to work at various different problems at different angles and different requirements, which are like good challenges to solve. If you don't have a good challenge, how do you better a system? That's how I look at things. The goal for our platform inside the company is to scale with size, volume, but also throughput. And for these aspects, a lot of time there was a buzz around Hadoop, Edgebase, and a lot of these technologies came in new. But nowadays, everybody is out there. Every other month, there's a new database coming out, and there are a lot of different options available. So how do we stay current? What is the next future that we can deliver so that our clients, which are internal developers in the company, internal product and business teams, can deliver rich applications? And now, milliseconds is not enough. People are asking for microsecond latencies at complex queries. And these query patterns are not enough to be like, I have 1 secondary index, 2 secondary indices. How many are you going to create at the end of the day? We need to support different complex query patterns. Businesses are complex. And everybody is now having more and more data. So in today's talk, we'll focus on 3 things. First piece is our Big-SQL query infrastructure requirements and how did we come towards designing the system. Second piece is going to talk about Phoenix Query Server that we have built on top of Spring Boot. My colleague Gabriel over here will cover that section. And the third section is in-memory SQL. How do we scale from milliseconds to microseconds with complex queries? And there's a third piece of our talk. Both these sections will have demos, and we'll represent with demos with performance numbers and see how they perform relatively in our environment today. Now, these are all very common points that I have listed over here. And if you go through these points, what you'll remember is RDBMS textbooks. This is standard RDBMS stuff. This is why RDBMS exists, because data model, query patterns, app developer needs, all these things keep on changing every day. And as businesses evolve, their requirements change. And we cannot have a static structure. And that's where SQL is still the king today. It gives us the flexibility to change applications quickly and deploy them to production and get things changing fast with a good turnaround time. The core piece that we are hitting with SQL is us as infrastructure teams and infrastructure developers can provision a framework where applications are decoupled enough that they don't use Edgebase APIs. They don't use any engine low-level APIs. They use an indirection layer. So with that indirection layer, they can build resilient and, more importantly, repeatable architectures. That's the key piece. We want repeatable architectures. If a team comes to me today, they want to go to production in 1 hour, go for it. That's the guarantee that we try to provide. Now, one of the key challenges with Big-SQL infrastructure, if you have used Phoenix or Edgebase with JDBC driver or Edgebase with just native APIs, build an application with it, and if you see the dependency chain and everything that it pulls in, it basically pulls in the entire universe, and you have like a really fat driver. If you have any conflicts in your own libraries, best of luck going through that. So this is why it's important to have a thin query server. We did it a few years ago. It made application development simple for our developers. The same initiatives were done with the PQS project. And we will go into PQS internals, explain the guts of PQS, and then go through how we changed it and what we pieced from there. Second piece is, as everybody, we have interns. Interns sometimes screw things up. For example, you need to protect things from interns, or more importantly, a random process, a rogue process. We need to build rate limiting, circuit breakers, and these are not options right now. These are standard pieces of an infrastructure stack that everybody needs to think about while developing their frameworks. The other piece is, if you're delivering query resources, we need to do affinity routing. We need to do load balancing. We need to make sure that if team A versus team B is using our query infrastructure, they are getting fixed number of resource pools. And how do we budget and align for them? Yes, we can always write all this code all over again, but the repeating theme we are going to go today is let's reuse everything that's already out there today, not just keep on building stuff for the future. And the most important thing we'll hit on today is query caches and in-memory SQL. That is where we go from milliseconds to microseconds at fast compute. So going ahead, my colleague Gabriel will cover a lot of the Phoenix stuff.
Thank you, Annie. Hello, everybody. My name is Gabriel Jimenez, and like Annie said, I'm an infrastructure developer in his team at Bloomberg. Before I go into the nuts and bolts of the talk, here's the obligatory slide on what is Apache Phoenix. I'm sure you guys have seen this slide many times today, heard everything on it. The main thing I want you to take away from it is something that our team really takes to heart in the Apache Phoenix philosophy, and it's that we see Phoenix as recipes for best practices on how to use HBase. And yes, Phoenix does sit on top of HBase, and it is a SQL layer, but more and more it's becoming its own SQL engine with its own improvements on the quality of life features that it offers. Secondary indices for point lookups and range scans on non-primary key columns, or user-defined functions that allow you to run business logic through simple SQL commands. And even ease of integration with data analytics frameworks that can then leverage the high read performance and that with the features that they themselves offer. But to better understand how exactly Phoenix sits on top of HBase, we think it's more important to see a architecture diagram. So here in our application architecture diagram, we have our application at the top, and the application has Phoenix as its data storage solution. And as Annie mentioned, this application needs to embed the Phoenix client as a dependency. The Phoenix client is itself a JDBC driver, and it also then embeds the HBase client underneath. It then leverages this HBase client to communicate with the region servers, the same HBase region servers, using the same RPC calls that HBase uses underneath. These region servers have also been augmented with some Phoenix RPC endpoints and some Phoenix metadata tables. One slight issue that might crop up with this architecture, like my colleague Annie mentioned, is that if you have a very lightweight application at the top, like is so often the case nowadays, and you end up embedding your Phoenix client, it might be the case that the Phoenix client actually dwarfs the size of your application, and wherever you deploy that application, you have to carry the dependencies with you. One solution that the Apache Phoenix group offers is the Phoenix Query Server, or PQS for short. And we would like to show the architecture to see how it changes once you put that into play. So the biggest difference between the previous architecture and this one is that we've decoupled the Phoenix thick client, per se. The Phoenix Query Server has added a layer of indirection between the application and the region servers. In this case, at the top, the application not only needs to embed what we call the Phoenix thin client, which is really just a remote JDBC driver with minimal dependencies. This is then used to connect to the Phoenix query server, which then embeds the actual Phoenix client itself and the HPX client underneath. To really understand the Phoenix query server internals, though, we wanted to focus and kind of just go through the connection between the application and the Phoenix query server itself. So we have a more descriptive diagram ahead. So in this diagram, we've changed the orientation a bit, so let me kind of describe it first. On the left-hand side, we have the user and the application. And then on the right-hand side, we stripped away anything that is not the Phoenix query server. So unseen here is the rest of the Phoenix HBase architecture that you saw in the previous diagram. The right-hand side is simply the Phoenix query server. Okay, so before breaking it down, the way PQS is implemented is actually, it's built on top of a Avatica server. So in order to understand its internals, we first need to understand 3 core concepts of Avatica server. These core concepts are what is a meta, what is a factory, and what is a service. The concepts of meta and factory are very closely tied together. A meta is simply just a set of local APIs that tell you exactly how to implement a particular functionality. And then a factory is the component that then augments this meta with the JDBC classes that correspond to an existing JDBC data source. This augmented meta is then fed to a service, and this service implements the functions of this meta in terms of request and command terms. Request and command objects. So specifically for the PQS, on the left-hand side we have the user, and they're making use of their application, and the application is trying to make a request to the Phoenix query server. This request actually hits the Avatica remote JDBC driver that sits on the thin client. This JDBC driver is going to make a remote procedure call over to the Phoenix query server using HTTP protocol and serializing using protobuf or JSON. When that request hits the Phoenix query server, it is actually handled by the embedded Jetty HTTP server that comes with the Avatica server that PQS is built on top of. Jetty is going to pass that request down to the Avatica service. This service on startup was brought up using what we call the Phoenix JDBC meta. And that meta is what will dictate exactly how this request is handled. Primarily in this case, the request is simply just going to be passed down to the rest of the Phoenix HBase architecture in order to be handled properly. Once that request is handled, a response will come back to the Phoenix query server. And then that response will be then transmitted back to the application using the same protocol that was used for the request and the same serialization that was used as well. Once the application has the response, it can do as it desires with it. Now, that last bit there with bringing back the response to the application at the end, I think really highlights the purpose of PQS, which is to facilitate pluggability of the Phoenix client into applications as they are nowadays. In our team, we use Apache Phoenix extensively. So we look to PQS as a way to facilitate application development and maintenance. So we really wanted to bring it aboard into our platform. However, before I go into how exactly we integrated PQS, I want to talk about another technology that is very deeply intertwined with our development workflow and the features that we already offer to our clients, to our users. And that is Spring Boot. Annie briefly touched on it in the introduction, but Spring Boot is a Spring project. And we really love Spring Boot because going back to pluggability, it really emphasizes lighter containers. It allows you to spin up and deploy your standalone application without much fuss or overhead. And it also allows you to use Jetty, Tomcat, Undertow, any of the 3 without tying yourself down to any which one. And it also enhances your developer experience. It has a lot of automatic configurations of third-party libraries wherever possible, and also operational simplicity by giving you production-level features like metrics or health checks out of the box. And so if we wanted to bring PQS into our platform, we first had to turn it into a Spring Boot application. But we also saw this as an opportunity to improve on PQS, as we thought that turning into the Spring Boot application would increase its pluggability, as it would become a standalone application. And it would also allow it to easily extend existing Spring projects in the Spring ecosystem and leverage any of the advantages that they themselves might offer. Okay. All right, so how did we turn PQS into Spring Boot PQS? Not the most original name, but whatever. The first part is we identified that the Avatica classes were the key to PQS, and we had to then turn them into components in a Spring Boot application. On the left-hand side, we have what we call the Avatica controller. This Spring component will hold the Phoenix service that runs in each of the Phoenix query servers. And this component will also handle any requests that come into the configured endpoint. On the right-hand side, we have a bit of our initialization logic that handles the three main Avatica concepts: the meta, the factory, and the service. This initialization code will prepare our application to essentially be ready to go when you turn it on. And with just these two things, your application is pretty much done. And we'll showcase how simple it is in a demo in a few slides. Now that we have our Spring Boot application, we can actually leverage another feature of Spring Boot, which is the concept of custom starters. Custom starters allow you to take a Spring Boot application and essentially turn it into a plugin. Once it's a plugin, this application can then be extended by other Spring Boot applications really easily and use all of the features that it offers. Not only that, but since Spring Boot PQS is now in the Spring ecosystem, we can also extend ourselves existing Spring projects with very little work on our end. And here's a list of some of the projects that we thought were useful. And as a matter of fact, some of these projects actually offer solutions to the problems that my colleague Annie mentioned at the beginning of the talk. For example, if you have pesky interns and you need to improve your fault tolerance, you could use Cloud Circuit Breakers Hystrix. This would allow you to stop cascading failures that could bring down your whole architecture. And then if you want reactive and programmable routing, you could opt for Spring Cloud Gateway. Or even load balancing and security for multi-tenant-based allocation of resources. You could have Cloud Security or one of the plugins that it offers. There's many more projects, and they all offer possible solutions to industry-level problems. If you'd like to check them out, there's a link on the slide. Now here, we see what we call the Big-SQL query architecture. This is what we envision the whole project to look like in the future. On the right-hand side, you will see the Spring Boot PQS that we described previously, but the rest is kind of the other Spring projects that we could bring in and the different layers that they could influence. But the most important part is that on the left-hand side, the user and the application have not changed. They're none the wiser. The user's still using their application, which just has the thin client, and there's also the SQL line functionality remains the same, and they're passing the same requests over. Now, here, I would like to showcase a little demo, or two little demos, on how simple it could be to bring up your Spring Boot application and showcase it is functionally the same as the existing SQL thin client. So the first demo. Okay. All right. So in this one, I'm just going to boot up the Spring Boot PQS. The first step is obviously to bring up HBase. Once HBase is up, I can start up my Spring Boot application that will bring up my service. This takes a couple of seconds. Once that's done, in order to show feature parity, I would then try to start up the SQL line command line client or command line tool, and then create create a table and upsert it with some data. The application is now up and running, so then I will switch over to the command line and try to initiate the SQL line command line tool with the Python script. And I'm passing serialization flag as protobuf, and the endpoint is very similar to the default endpoint that you would use, except that it has proto at the end. So here, I've already connected don't think it's necessary, but here's a little zoom in for the command line. So if you can see, it looks exactly the same as you would expect your SQL thin client command line interface to look like. Right. Next, I will try to query for some data on the systems tables to make sure that everything is looking A-OK. Right. I see what I expect. And then I will try to create my table. So these tables that you see here are the metadata tables that I mentioned that your region service will be augmented with once you're using Phoenix. So my table was created in roughly 2 seconds. I mean, I'm running everything locally, so I'm not expecting the most performance at the moment. This is just a functional parity check. I've observed it with 2 rows, just 3 columns and some dummy variables. We got an integer, we got some strings, and we got some characters in there. And I select star from my table. Everything is there, hunky-dory, and now we'll exit out of my SQL Thin client or command line interface and be happy. All right. So that shows us that you can use it the same way you used it before without much change on your end. And then this demo will actually be a little bit more nuanced. We have put some breakpoints into our startup of our application, and we will stop at each one of them and kind of give a little description of what they highlight. So let me bring up the magnifying glass. All right. So here, the first order of business, this is the code snippet that I showcased on the slides. The first order of business is, as you would expect, to bring up your HBase configuration. Nothing out of the ordinary there. The next step would be to define your factory. This is something that the Phoenix codebase does already. So we created our meta. This is the creation method. This is all the configurations that will dictate exactly how we handle requests and what we do with them. Once that is done, we go back to the main code and initialize our service with the meta. Now start up our application, and we're pretty much ready to go. Application's booting up at the bottom left, and we should be done. The next step that we'll showcase is we will then try to fire up the SQL line command line interface, and then we will see what exactly happens there. Essentially, what we'll showcase is that we're receiving a request to start up a connection. And we see that here. And very easy, this is the Avatica controller component that I showcased on the slides earlier as well. Here you see that it's hit my proto endpoint, and I'm just receiving a byte array request, and I'm going to have a byte array response. You actually will see multiple requests as the application is booting up all the necessary components to start up a connection and then maintain a connection handle. And once that is through, I will switch over to the terminal, and you will see that my SQL Thin command line tool has started up as expected. There we go. And that is pretty much all she wrote. The next thing I will try is close the command line tool. I will receive a response to close the connection. That one's much simpler, just one request. And once I switch back to the terminal, my tool will have exited correctly. Yep, that is it for that one. All right, switching back here. Uh-oh, how do I? Let's go here. Let's hope that works. Perfect. All right. Next, okay, so we took this tool and we gave out our platform to multiple users to play around with and kind of address their current use cases. Once they were done with that, they got back to us with a set of feedbacks and requests. The first set of feedbacks, as anyone would expect, is they want it to be faster. Oh, okay, cool. The second one is a little bit more nuanced, obviously. It's as their current use cases were met, they came up with new use cases because they want to keep their jobs. So then their use cases became more complex, and in turn, the queries became more complex. This meant that their queries were no longer on index columns, and they may have particular grouping or ordering that made that hurt their performance greatly. And some clients even voiced the need for query notifications or query callbacks on pending predicate matching. To hear more about how exactly we address these requests and the technologies that we use, here is my colleague, Rohit.
Thank you, Gabriel. Hello, everyone. My name is Rohit, and I'm a software engineer at Bloomberg. So now we're going to talk about Apache Ignite, which is also a Spring project, and how we integrated Apache Ignite with Spring Boot PQS for better query performance. So based on the feature request in the previous slides, like faster query execution, executing complex queries, getting faster table scans, we realized that we needed some sort of caching technologies so that we can get faster access speeds, like read and write speeds. Now this is precisely where Apache Ignite comes into picture. So what is Ignite? It is an in-memory distributed cache which also acts as an in-memory distributed database. You can configure Ignite to not only store data in the memory, but also in the underlying persistent storage device. It is capable of processing analytical and streaming workloads, and it works and it promises great speed even at petabyte scales. So now we talked about the different features in the previous slides. The feature that got us excited the most was Ignite serving as a distributed database, which also supports standard SQL query semantics. This facilitated transparent client integration at our end. Therefore, client code that is executing SQL queries would transparently execute it over our modified Spring Boot PQS that has Ignite within its stack, and it won't even realize that there is a caching layer in between. The only thing that they would get is better query performance, which is all we need. There is also a demo where we illustrate how we can use the provided SQL thin client that comes bundled with Apache Phoenix, and we demonstrate that without even changing a single piece of the client code, we were able to communicate with the new PQS server that is integrated with Ignite. Now, apart from that, it also supports query notification, which was again one of the features that was requested by our clients. Here, user can set a predicate on which they want to get notified whenever a data that matches the predicate gets written on the cache. So now, let's talk about how we integrated Ignite with the Phoenix query server architecture and how we were able to achieve the transparency that we talked about in the previous slide. So I'm going to concentrate on the part of the stack that changed. Now, in the previous slides, as Gabriel mentioned, whenever a SQL query request comes from a thin client, it hits the Phoenix query server. The Phoenix query server then talks to the Phoenix JDBC, which talks to HBase to get the required results. Now, in this new architecture, we are putting Ignite JDBC or the Ignite cache in between PQS, in between Avatica and Phoenix JDBC. So now when a SQL request comes from a client, it is handled by Avatica handler, which now instead of delegating the call to Phoenix JDBC, now talks to Ignite JDBC. The Ignite JDBC on its own and now then understands the SQL query and runs the query over cache. And this is where we get the result and the SQL and the good performance that is promised. If required, Ignite cache can also delegate that query to the underlying Phoenix JDBC, which will talk to Phoenix and execute the query. Now, if you notice at this between the Apache Ignite thin client and the PQS, we see that nothing changed. The thin client still talks to SQL, still talks to the PQS server over SQL, and this is where we achieve the transparency or the proper integration that we talked about. So the existing client code that still talk to PQS and issue SQL command can do the same without even changing their code. Now that we know that where the caching layer is integrated inside the PQS stack, let's talk about the different ways we can set up Ignite to serve SQL queries better. So first, let's talk about the in-memory SQL cache setup. So this setup is provided by Ignite out of the box. As the name suggests, in this implementation, the SQL queries are actually executed directly over the cache. So any data that resides in the cache is over which the SQL query gets executed. This means that all the data set first needs to be loaded inside the main memory, which again brings along with it a set of constraints that the entire data set should be small enough or relatively small so that it can be pulled into the memory. Now, based on the SQL, based on the SQL query served, based on the SQL queries that will be served, again, like I told, since everything will be in memory, we can this type of setup can accept any sort of workload like high read or high write request, because everything will be executed in the memory. This type of setup can also be configured so that write queries like DML queries, like absurd queries or insert update queries, could then be updated on the cache and also inside the underlying database. We'll talk about and showcase these features in the upcoming demos. Now, let's talk about the other setup. Now, we realized that in the previous slide, there was a shortcoming with the in-memory SQL query setup. We need to load the database, the entire data set in the memory. But what if the data set is huge enough that we cannot load that in memory? To avoid or to cater to such use cases, we came up with Phoenix Query Cache. So this type of setup is not provided by Ignite out of the box. Therefore, we implemented this setup at our end. So in this approach, when a SQL query first hits the cache, we check if the result set associated with the SQL already exists in the cache. If that is the case, then the result set is returned from the cache itself without ever hitting the database, and that is where we get our performance. If the SQL query or the result set associated with the SQL is not in the cache, we'll execute the query on the database and return the results back to the user. On our way back, we'll again cache those data so that in the future, when the same SQL is executed on the cache, we'll just return the data from the cache itself. Needless to say, there could be a scenario where this type of setup could return stale data or stale result set. This could happen if there is a client query that is running some sort of DML queries and update the database in the backend. So for such scenarios, we need to make sure that if any sort of modifications happen on the result set or happens on the database, we invalidate our cache. This means that whenever a write happens, we clear out the cache, and so any SQL queries or SQL select queries that get executed from there will now be hitting the database so that we can get the latest results. And again, these latest results will be cached until a new write again comes in. So based on this setup, it is quite clear that it is suitable for low write and high read environments, because the less writes you have, the less number of times your cache will be invalidated. Again, when you have high number of reads, it is better if you have the same set of SQL queries that gets executed, because in this way, you'll never hit the database and most of your requests will be served from the cache itself. Now that we know both the setup, let's see a quick demo and see how both of them work. Can you guys see it? Okay. So we are now demonstrating the in-memory SQL setup that we talked about. So on the left-hand side, we have the plain simple JDBC. We have the plain simple client that directly connects to Phoenix over JDBC. On the right-hand side, we have the SQL thin client that connects to Phoenix query server with Ignite built in. Again, this Ignite is currently behaving as an in-memory SQL. So all the data is right now loaded inside the memory. Now, if you notice on the right-hand side, if you see the SQL line thin.py file, like these files came bundled with Apache Phoenix, and we did not change anything. All we did was just supply the URL so that we could talk to the Ignite PQS server. Now, let's connect to both this Phoenix using JDBC and PQS. So let us just check if the table actually exists. So we are currently working on a person table. And it has approximately 1 million rows. on the database, and it has about 11 columns. We'll check the same table on the PQS end. Again, these tables are currently hosted on the Ignite side, and you'll see that there is only one table because that is what it was initialized with. Again, I'm saying that before this demo, we hydrated the cache with 1 million rows, and we have excluded from the demo. So now we are going to execute a simple count star command and see how much time it takes on Phoenix. We're gonna execute the same query over Ignite and see how much time it takes. So it took about 3 seconds on the Phoenix sides, or about 3000 milliseconds. On the thin client, when we execute the same query, we see that it took about 33 milliseconds, which is a huge improvement. Now we're gonna run a query where we have the search predicate, and the search predicate contains the primary index. So here employee ID is the primary index, and we execute the query on the Phoenix end. It takes about 140 milliseconds. Now it takes about similar time on the Ignite end too, but we have seen that when the data set is more, Ignite performs better than Phoenix. Now we are going to run a query where it will do a full table scan. The columns that are used in the query is not part of any index, so we'll do a full table scan and then filter out the results. Obviously, it's going to take a lot of time in Phoenix. So we have executed the query already on the JDBC end. Let's see. So we're going to execute the query now on the thin client side, and we see that it took about 1 second to execute the same query, or 1000 millisecond, and it took about 13,000 millisecond or 13 second to execute the same query on the Phoenix side. So you can see the performance improvement that you're getting by merely adding a caching layer in between, which supports standard SQL semantics. Again, we are executing the same query, so nothing has changed. Now, we are going to demonstrate that when we write a DML query, or where we modify the data inside the cache, how we can configure the cache to also modify the underlying database. So in this case, when I issue a delete command, it will update the cache, and behind the scenes, it will also update the database. So now we have 1 million rows. After the delete get executed, we'll have one less row. So again, a count star will return one less row, and if we execute the same count star on the Phoenix end using the JDBC driver, the number of rows are reduced. So we see that the write requests were carry forward, and therefore we configured it as a write through cache. So now let me showcase the other setup where we are using Phoenix as a query cache. So in this setup, again, on the left-hand side, we have the Phoenix JDBC. Like the Phoenix JDBC drivers, or the Phoenix client is directly talking to Phoenix using JDBC. And on the right-hand side, we have the thin client that is talking to our modified version of Apache Ignite with Phoenix Query Server. So we're going to run a simple count star query and see how much time it takes. Now we're going to notice, after running the count star query, that initially both the JDBC and the query cache setup would take the same time, because the select query is currently not in the cache. But if we execute the same select query or select count star query again on the cache, we'll see that it takes less time now, because the data is directly returned from the cache. Now we are going to run the same set of queries, query which contains a primary index in the search criteria, and see how much time it takes. It took about 192 milliseconds, similar time. But if we execute the same query again after caching it, it is still better. It takes about 60 milliseconds. Now we're going to run another query where there is no index in the search criteria, and we're going to demonstrate how much time it takes. Sorry. So it's going to take a lot of time probably because there is no index. So we're going to execute the query on the JDBC end, and now we're going to execute the query on the query cache end. So it took about 7 seconds, and again, it is going to take the same amount of time. But if the same query is executed again, instead of hitting the database, this time it will return the data from the cache itself. So you see that from 7,700 millisecond, it went to like 90 or 90 millisecond, which is again a huge improvement. So for any complex queries, no matter how complex it is, as long as the result set can be cached in the memory, we'll always get consistent performance. Now let's talk about cache validation, invalidation, sorry. So if we execute any sort of DML command, it should invalidate our cache because the result set will be stale. And this is exactly what happens. We run a delete query, and then if we run any sort of select queries, we'll realize that the select query will take the same amount of time as the Phoenix client. So here, because the cache got invalidated, it will again hit the database, get the latest result set, and cache it now. So if we now execute the same query again, we see that now this time it has hit the cache again. So this is where we demonstrate the cache invalidation part. So let me jump back to the slides. So we're going to talk about the relative benchmarks here. This relative benchmark slide is just to showcase that given a hardware on which Phoenix is running, how did the query perform when a caching layer was added in between. Now the latency numbers were taken on our prototype clusters. The numbers might be different for your configuration, but what we want to point out is how the performance of a query improved by merely adding a caching layer. So in this in-memory SQL setup, we see with 1 million rows and 11 column table, we see that when a query was executed with index, it took about similar time, but still there was a mere improvement. But when a query without index is executed, we see that there is a factor of 10 improvement, which is a big deal. Now we're going to talk about the next setup where we use query cache. Phoenix is a query cache. Again, we used the data set size was 1 million row. We had 11 columns table. Now in this case, we need to consider cache hit and cache miss. Now when there is a cache miss, of course it will take the same time as what Phoenix took, or even more sometimes. But if there is a cache hit, in that case all the result sets is directly returned from the cache itself, and therefore we get the performance boost. So again, while executing query with index, the relative improvement is like 3 times, and when we are executing query without index, the relative improvement is like 165 times, which is really good. So one thing that I want to note here is no matter how complex the query is, the moment it is cached, it will consistently return the same latency time. So now that's all from our side.